Dudes, friction, number 2, let's do it. A 7-kilogram aluminum box is being pushed across a steel table that is 4 meters long. I say aluminum and steel because aluminum and steel have a specific coefficient of friction. The UK, the coefficient of kinetic friction of aluminum on steel is 0.47. Notice there are no units on that, there aren't supposed to be, it's just a modifier. The box is being pushed with a force of 40 newtons. On your worksheets, it says, I believe, 17 newtons. That's wrong, change it. The problem doesn't work if it's 17. Should be 40. What is the force of friction resisting the applied force? Also, what is the net force? And what is the resulting acceleration? And lastly, if the box begins from rest, how long will it take until it is pushed off the table? So clearly, we have both a forces problem and a kinematics problem. I know the variables I use for kinematics, so I'm going to go ahead and write them down. You should too. Do it with me. S, xi, vi, vf, a, and t. Beautiful, beautiful, beautiful. And then, I know I have forces going on here, specifically forces of friction. So I'm going to draw a free body diagram so I can get all of my forces straight. I want to know all the forces that are acting on this aluminum block. So aluminum, Al, got force of gravity, and I have a resulting force normal because the table is pushing back on the block just like the block is pushing on the table. It's not moving up and down, so they're balanced. And then I've got a force pushing it that way. And remember, on free body diagrams, we should be pushing our blocks this way. Our arrows shouldn't be on this side pushing in, they should be on this side pulling out. Great! Let's see, that would be our force 1. And then we have a reactionary force of friction. Exactly. Okay, so let's write those forces out. So force normal, force of gravity, force 1, and force of friction. And then let's go ahead, since we've got a force 1 and a force friction, and we know ahead of time, I mean, we're looking at this and it's clearly supposed to be in motion, so there's got to be some amount of acceleration going on here. So we know that we're going to have an F net that's going to be the difference between these two. So we'll go ahead and put in that variable as well. F net. Why not? And then we have a coefficient of friction, so mu K. And it's kinetic friction, we know that already. And then we've got a mass, so mass 1, just in case we end up having another mass, a second mass. I don't want to deal with multiple of the same variable, so I'm going to say M1. So let's throw our numbers in there right away, just so that we don't get confused. So M1, 7 kilograms. Easy peasy. And then, let's see, UK of aluminum steel is 0.47. 0.47. Oh, you know what? Let me go ahead and throw an acceleration due to gravity on there, just for pity's sake. Beautiful. 9.8. Negative 9.8. Can't forget that. The box is being pushed with a force of 40 newtons. So my F1, 40 newtons. Excellent. And what else? What is the applied force, net force, acceleration? That's all I know. Those are all the variables I start with. Whew, man, that's a toughie. So we're going to need to figure out the force of friction so that we can figure out the net force, because that is, what is the force of friction? Or no, we need to know the force of friction and then the net force. So we're going to need to know the force of friction. To know the force of friction, we got to know the F normal. To know the F normal, we need to know the force of gravity. Okay, great. So let's go ahead and calculate that. Okay, so let's go ahead and write out our equations and then make an easier one. So I know that I need force of friction. Force of friction can be equal to mu K times force normal, and it's going to be the negative version of that because I'm generally going to always be dealing with a reference point like this. This is negative, this is negative, this is positive, this is positive, right? Well, my force normal is going up, so it's going to be positive. My force of friction should be going backwards, so it's going to be negative. So I need to make force normal the negative version of it, right? Okay, well, what's force normal equal to? Force normal is equal and opposite, so positive, negative, of the force of gravity. Okay, well there we go. And then force of gravity is equal to mg. Great! I can actually just combine all of those. So I could insert mg over here, equals negative mg, and then I can plug, because Fn is right here, I can plug this in for that. So then I would have F of friction is equal to negative mu k of negative mg. Well, negatives cancel each other out in this case. That's fine. Because g should be negative 9.8 because it's going down. I'm going to end up with a negative friction then. Great. So, force of friction is equal to my mu k, which is 0.47, times my mass, which is 7 kilograms, times negative 9.8 for acceleration due to gravity. And what is that number, ladies and gentlemen? 32.2. So it's going to be 32.2 newtons is my force of friction. I hope now you see why I changed it from 17 to 40. 32, that's negative 32.2 newtons. Great, well there's our first answer, right? Part A asks what's the force of friction. There we go, 25% done. And then what's the F net? We want to know the net force. Well, the net force, we've got two ways of describing it. Net force is MA, right? That's always going to be true. And then F net is also equal to the sum of forces. The way we write the sum of forces is this little Greek letter called epsilon. It means the equilibrium of forces means the sum of all the forces, and it's going to come up a lot in applied physics and when we get into equilibrium problems. You don't really need to know what it means right now, but it just means like F net is equal to the sum of forces, which is also F1 plus F of friction. So we're just going to combine those. That means the same thing as this. It means the same thing as that. Easy peasy. Okay, so F1 plus force of friction. So 32.2 plus 40 is going to give me 7.758 newtons. Okay, not exactly, but close enough. 7.8. 7.8 newtons equals F net. And that is the second part. Excellent. Then, what is the resulting acceleration? Well, remember, F net is also equal to ma, so I can easily find the resulting acceleration because I've got F net. Great. So let's go ahead and write that one out. Let's make some room for ourselves. So F net equals ma, so 7.8 is equal to 7a. 7 is my mass. Nice. So 7.8 divided by 7. See, these problems, once we set them up the right way, they're really easy. This is why I hammered setup in the first part of our class, because I knew once we got to forces, we'd have a lot more variables, but they'd be really easy to work if we set it up the right way. So if you just take some time and set everything up the right way, you're gonna have a really easy time. Our resulting acceleration is 1.11 meters per second squared. Okay, 1.11 meters per second squared. And that was the third thing I wanted to know. And then, if the box began from rest, how long will it take until it is pushed off the table? Well, I forgot to put that one in, 4 meters. We know that the table is 4 meters long. So, how long will it take, starting from rest, which is 0 meters per second, how long will it take to accelerate off the end of the table? Well, I can figure that out pretty easy. Xi, we're going to call it a big fat 0. And then we have our S equation. We've used this tons of times before. Okay, well, my Xi is going to drop out. My VIT is going to drop out because VI is 0. So then I'm going to have S equals 1/2 AT squared. Beautiful. So let's go ahead and plug in our numbers. So, S is 4 meters. It's equal to 1/2 and acceleration is 1.11 t squared. Great. So we'll go ahead and multiply 1/2 by 1.11 and then divide 4 meters by that result. 4 equals 0.555 t squared. It's going to get me 7.2 equals t squared. Square root of that is 2.68 seconds equals t. And there's the last part of our problem. 2.68 seconds. This thing is resolved. Excellent. Thank you.